there was a numerical mathematician, very famous, now no longer with us, Ghil at Stanford, who used to say that it's obviously redundant to introduce the speaker. Everybody's in the room because they know who the speaker is, so one should introduce the audience. You know. So this has been a great audience so far, and I hope you'll stay that way. Okay, so yeah, I can see it there, but I have to point there. So let's see. But will this? No, this will not.
I think you have to put this.
Where?
It's lost, of course.
Ah, no. Where is?
The last person in charge was Tamash. The pointer. You ate the pointer. No, yeah.
Yeah, I know.
Yeah.
Non, il manque, justement. Oh, okay. Okay. Terrific. Okay. So, yeah, good. I'll be talking a little bit about one of the main reasons for having organized this entire trimester, which is my fundamental belief that this is important for understanding climate change by taking care correctly of climate variability. And if you're interested in any of this, you can find more at these websites. So actually, the full title that I had given was The Eruption of Non-Autonomous and Random Dynamical Systems into the Climate Sciences. But actually, yesterday, we had a sequence of 3 talks by the group of Tamás Tél that you know, was an important companion group in this eruption. So I decided to shorten the title a little bit. So this is based on joint work with many students and colleagues to whom great thanks. And there are actually quite a few of them in the room. I'm sorry that Mikhail couldn't be here, but I'm delighted that Fefe Jin is here, and Valerio, and Denise, and of course Yuzuru, although he didn't talk about what we are trying to finish together. And I don't know, some of these people are going to, I'm going to show some slides, are going to be next week here if they're not here now. Okay, so yeah, I'm sorry about not following the transition of showing the portraits of all of them, but that would take some time. So the outline is intrinsic versus forced variability, multiple scales of dynamics, climate sensitivity, both in the usual equilibrium version, and especially the less usual, but becoming more so non-equilibrium version. A little bit about non-autonomous and random systems, which, as I say, have been covered by now by a few other speakers. Pullback, snapshot, and random attractors, and tipping points in this setting. And then just 2 little climate applications out of many. So this is a Lorenz without a T, 1963 convection model with random forcing, affectionately called by its followers LoRa. And then something about the El Nino Southern Oscillation and Arnold tongues and pullback attractors, and then some work in progress on non-equilibrium climate sensitivity and the topology of LoRa, including remarks and bibliography. Okay, so again, motivation. The climate system is highly nonlinear and quite complex. That's motherhood and apple pie, as they say in the US. The system's major components, the atmosphere, oceans, ice sheets, etc., evolve on many time and space scales. The predictive understanding of this system has to rely on the system's physical, chemical, and biological modeling, in other words, on all the details and all the boxes in the diagram, but also on the thorough mathematical analysis of the modes that's obtained, the forest versus the trees. And I must say that, you know, another way of talking about this is that, you know, there are rabbits, there are hedgehogs and foxes. You know, the hedgehog knows one thing, how to roll up to defend himself, and the fox knows many things. So anyhow, let's say that the more holistic point of view and with a mathematical and physical perspectives has evolved quite a bit over the last few decades. But still, this hierarchical modeling approach is not followed quite consistently throughout the community, and I think it should be so a little bit more. It allows one to give proper weight to the understanding provided by the models versus their realism, in other words, back and forth between toy or conceptual models and detailed realistic models, and between, of course, models and data. I'm putting toy into quotation marks because, of course, the people who do the detailed ones sort of look down their noses at people who do the little models. I remember a very distinguished member of our community who once told me at a National Research Council meeting in Washington, you know, Michael, you don't want me to really take your little models seriously. You know, she's been one of the people who really deserved the distinction of the Nobel Peace Prize. On the other hand, I put here realistic into quotation marks because the people who do the big models think that they're realistic. But of course, you know, while they are based on fundamental principles of physics, conservation of mass, energy, momentum, etc., they are not really entirely what's called ab initio. There are a lot of so-called parametrizations and a lot of semi-empirical parameters which are known within a factor of 2 or even within a factor of 10. So I don't want to insist on this point, but anyhow, you know, I should give up this little somewhat aggressive dialogue and collaborate more. So how do we disentangle natural variability from the anthropogenic forcing? Should we, can we? And of course, yes, we can. Just to give you a very simple example, you know, in the case of ENSO that, for instance, Feifei Jin here has made important contributions to, it's very hard to say what's natural variability and what is you know, global warming, because the tropical Pacific, depending on exactly how you define it, is about 1/3 of the surface of the globe. So when you have an El Nino, that has, you know, is reflected in the global temperature. Okay, so we really need to understand this. Okay, so intrinsic versus forced variability and multiple scales and climate sensitivity. Okay, so I think, I don't know whether Freddy Boucher is still here, but this is the quote that I was alluding to when he showed us a certain slide. This is paraphrasing. So this, you know, John von Neumann is, of course, very well known in the climate, in the weather and climate community because of that famous first experimental forecast, Schweinfurth von Neumann. And, you know, recognizing that numerical weather prediction is one of the most important applications of peacetime computers. But this is somewhat less well known. He also gathered a meeting just before his untimely death at Princeton. And actually, as far as I know, this book, which was only published after his death, 3 years after the meeting in 1960, has the words dynamics of climate together, for, I think, for the first time. Okay? So it says the initial value problem, numerical weather prediction, is the easiest one. That's the one that we know most about. The asymptotic problem, long-term climate, a little harder, but the intermediate problem, what's sometimes called low-frequency variability, in other words, lower frequency or longer periods than the ones of the most intense motions on the time scale of interest, involves, we know now multiple equilibria, long periodic oscillations, intermittency, slow transients, and what's now called, used to be called bifurcations and is now called more alarmingly tipping points. That's clearly the hardest. So, that's the one that we're trying to deal with. So again, this is a very popular diagram. There are many versions. This is out of an encyclopedia article of mine, but it was first was published by Mary Mitchell in the Quaternary Science Review in 1976, which coincidentally is the same year as a famous Hasselmann paper in TELUS. And it's an artist rendition of the climate spectrum, so this is variability. Of course, there's no single time series that extends to the entire length of the history of Earth and has a resolution of days or hours. These are superpositions of various pieces of information. But basically, it's made up of three portions. One, which is the continuous part of the spectrum, which is really most of the variability. And then there are some lines, so that's the point spectrum, okay? That's rotation of the Earth around its axis and revolution around the sun, or rather the center of the solar system, the mass. And then there are bumps. And the bumps are, controversial, but I think that there are reasons of hope because they reflect underlying Hopf bifurcations that get thickened, widened by climbing higher up in the bifurcation tree to more complicated types of behavior, but leaving a trace. And basically, there are whole communities which are organized around elucidating what's called intraseasonal, or these days S to S, subseasonal to seasonal variability, or this sort of stuff involves the ocean. This one involves El Niño Southern Oscillation. This involves quaternary glaciation cycles. And really, typically what one does when one works on something like this is one looks at the higher frequencies, the ones to the right of the piece that we're interested in as white noise, or what I like to call warm color. Typically, the assumption is red, but essentially there's more variance at lower frequencies. So that's what's done to the right, and what's done to the left is handled as slow, or in physical language, adiabatic evolution of parameters. So basically, what we're talking about now, non-autonomous and random dynamical system, is embedded in the way that we typically work on this diagram. But what we are trying to do is to do so in a more, self-possessed, self-consistent, deeper way. I also want, this is a citation, a literal citation out of Murray Mitchell's paper. No known source of deterministic internal variability, which was a state of the field. This was exactly 1 year after my PhD at the Krant Institute. Okay? So I think that looking back at these decades, it's what I've been trying to disprove, hopefully with a little bit of success. Okay, so this comes also out of that encyclopedia paper. And it reflects, on the one hand, the so-called equilibrium climate sensitivity point of view, or ECS, which maybe started with the report to the same National Research Council by a panel chaired by Jules Charney in 1979, so that's exactly 40 years ago. And the answer was, for a doubling of CO2, global surface air temperatures averaged over the seasons would increase by 1.5 to 4.5 degrees. Now that uncertainty has not been diminished. It is still with us, and it has rather been increasing, and that's sort of obvious why, because each time you add another knob to your machinery, you know, you expect this to grow. So the purpose should not be to try to reduce it, but to understand it better and to still be able to act with that uncertainty. So again, I don't need to tell the audience here that, you know, a scalar linear ODE, you know, the person who told me, I mean, we're good friends. This wasn't something personally hostile. But, you know, since I have to say she, you might guess who that was. But she probably deserved that Nobel Prize a lot more than Al Gore did. You know, this was still the interpretation of all those integrations with big GCMs by the time of the third so-called assessment report. You know, all those were interpreted in terms of this linear scalar ODE, and actually the first assessment report of the IPCC had chapters pretty much like this, where people, you know, were specialized in certain feedbacks and in certain sources and sinks of forcing. But of course, what we need to consider is this much more complicated picture, and that's what we're doing during this workshop and this trimester. Okay, so again, out of that actually fourth assessment report, there's this diagram which shows quite clearly that for each one of these scenarios, you know, the uncertainty is huge. And I don't want to take too much time, you know, over the last one, the fifth one, the situation is still pretty much the same. Okay, so getting on to non-equilibrium climate sensitivity. So this is sort of a schematic diagram out of the, you know, Charney et al. 79 and subsequent versions of equilibrium sensitivity. Global temperature in red and CO2 concentration in dashed blue. You know, it jumps, this clearly adjusts to the new level, okay? And you're done. So all you have to argue is exactly about what the sum of the k's is and what the q's are, okay? Well, what about non-equilibrium sensitivity? So let's say, for instance, that ENSO were purely periodic, which it isn't. It has a lot of the variance in the so-called quasi-biennial and quasi-quadrennial or low frequency components. They were purely periodic. Well, the average temperature is still going to go up. I mean, you know, in spite of efforts of various deniers, even of an educated one, to say otherwise, the iris effect and so on, there's no way really that the average will not go up. Okay? But what can still change, and what's also interesting, is the period, amplitude, and phase of the limit cycle. And I don't have to explain here what the limit cycle is. I usually have to. And then what I say here, what about some real stuff? In other words, chaotic plus random. So again, the mean will go up, but there's a lot of other things that will change. Higher moments, like distribution of extremes, etc. Okay. Yeah? No. No. We don't know. I mean, you know, the person I'm referring to is not here, but those who know who has come up with the iris effect, and that has been disproved conclusively. Okay? So.
Why are you being so coy? Why don't you name names?
Well, because it's, you know, it's like gentlemen don't read other people's letters, you know, you don't attack people who are not in the room, okay? But if you want me, you know, it's Dick Lindzen. I mean, Dick Lindzen doesn't only not believe in global warming, he also does not believe in the results of studies on the effects of smoking, okay? Although he has stopped smoking by now. Okay, so, okay. Just a little bit, because we've heard all these names, pullback, snapshot, and random attractors. I will come a little bit to that, and then to tipping points in this context, in this broader context of time-dependent systems, where it has a meaning aside from the rhetorical one. Okay, so every once in a while I have to do a beamer slide because there are too many equations. So the source, the sources of non-autonomous dynamics. So the main point is physically open, as we heard in Yuzuo's talk, physically open versus closed systems. So there are fluxes of mass, momentum, energy between the system and its surroundings, which are present or not. And so the mathematical framework of non-autonomous dynamical system is appropriate for physically open ones. So basically what I'm trying to emphasize here is that there are multiple sources in the mathematical and physical literature of the approach to this. So the first one, chronologically, is that the deterministic one of George Sell, which has passed away recently, of skew product flows. So you have x dot is equal to f and x and q dot is a function of only q and not of x. Okay, so so x is an RD and q is can be another space. So and the name used is the driving force for x. Okay. And then there are two complementary sources of pullback and snapshot attractors. This is the mathematical literature. Franco Flandoli was here for the course that preceded this workshop and gave a really beautiful lecture on why you have to take this pullback approach, while the usual approach of autonomous differential dynamical systems with forward asymptoting does not work. And I'm having a slide immediately after this. And then Chelsea-Grebogi and Ed Ott with postdoc Ramirez came up with something that has pretty much the same idea. So anyhow, here you have a stochastic differential equation, and again you can have this Q from here, and WT is a Brownian motion in RD, and the reason you have to write these separately, I guess everybody in this room knows, but not everybody outside this room, is that essentially dt is proportional to dw squared. Okay, as Yuzuo was showing, we know the Brownian motion has mean spread that's square root of time. So more generally, studying explicit time-dependent enforcing or in coefficients. So in the case of the atmosphere and oceans, it doesn't have to be an external forcing. The randomness can come from subgrid scale parametrizations. Basically, you can't resolve clouds, and you shouldn't probably, or various small-scale processes in the ocean. So you model anything that you're not interested in the details of. You can model a stochastic. So anything that has explicit time dependency for all coefficients requires NDSs. So the term, what's a little bit confusing is that the term non-autonomous is used both for the deterministic case following Sell, and he actually called them skew product because the skewness comes from the fact that this is independent of x while x is not independent of q. So and for a unified perspective on the deterministic and the random case. There are some technical difficulties in the two separate cases, but there's an attempt of having a unified theory. For instance, there's a book by Caballero and Han which explicitly tries to do this. So the commonality between the two cases is the independence, as I said, of Q, of W, of X, and the semi-group property, I'm going to come to this 2 slides from now, of the driving force, whether it is Q or T or W sub T. For instance, the stochastic literature, T is placed here rather than there. So likewise, pullback attractors is used both for the deterministic and the random case, while in the latter case, more specifically, the phrase random attractor is used. Okay, so now more specifically, much of the theoretical work on the intrinsic variability of many things, but I give this often in the context of the wind-driven ocean circulation work, which was presented in some detail last week by Stefano Pierini, who's still here, and that stuff is on his website. Okay, so the proper framework is this. So we do here with a toy model given by the, okay, so this is out of the title talk, but the main point here is that I wanted to make is a very simple pullback attractor. So again, you know, the x dot minus alpha x when sigma equal to 0 is what was in that scalar linear equation that I showed you, and we all know that the limit, the attractor is x identical to 0, but what about this? So in this case, you can actually compute it explicitly, but you know, the point that Franco was trying to make on the blackboard 2 weeks ago at some length is it's not clear how, you know, you say you're observing your system at a certain time, and how do you describe what happens at this time versus at this time, etc. So basically what you have to do, if I follow the picture here, is to pull back to a compact set and let it rip, and it goes to these various things. So let me just, if I manage to do this quickly enough, find the appropriate, okay, so Hong Hu is also here, from whom I have this little video, okay? So here you go again, okay? You pull back, pull back, pull back, and you see clearly that at each point, okay, at each point, as you pull back to s towards infinity, okay, you converge more and more to this. So let me just do it one more time, okay. You see how it converges. Say at this point, okay, as you go back, it converges, and the only difference between the definition of snapshot attractors in the physical literature and the pullback one in the mathematical literature is a rigor, mathematical rigor with which this pulling back is carried out. In practice, fortunately, you only need to pull back for a finite time, and it depends essentially how dissipative your system is, okay? So that's what allows you to actually compute these things numerically. Okay. So again, here I just have the references. Oops, sorry. I just have the references for the various things that I talked about. Okay, some general references, and the application. They're just one paper each from each one of the groups which has cultivated these applications with a particular dedication. Okay, so we have in the room, when they gave talk yesterday, all three of Gabor, Tomáš, and Tomáš. Okay, and then that's the paper that I mentioned for snapshot attractors, and of course Hans Krauel wasn't here, but Franco was. And there's of course a book by Ludwig Arnold, which is not very digestible. That's why in appendices to our work, we try to explain to a more physical audience, you know, how to understand what's there and what Hans Krauel and Franco Flandoli did. I understand that they're both postdocs of Ludwig, and he's told us an interesting story about how that famous paper came about. So random dynamical system, this theory is a counterpart for randomly forced dynamical systems of the so-called geometric theory of ordinary differential equations. It allows one to treat stochastic differential equations and more general systems driven by noise, as I showed, as flows in phase space cross probability space. Okay, so you know, these are the analogies between the stochastic and ordinary differential equations, random and so-called differentiable dynamical systems, but which implies autonomous, and Ludwig Arnold and V.I. Arnold, no family connection. I try to emphasize the difference by the usual transcription of the myak znak in Russian, you know. Okay. So the setting, this is just, I promised you a little bit more on the semigroup property. So here it comes. We have a phase space, think of Euclidean probability space, omega. So the sigma algebra of events, the sigma algebra of sets, is what the events are in this axiomatic theory of probability. And I just like to mention we are the guests here, not just of the Institut Henri Poincaré, but within it of the Centre Émile Borel. You know, Borel is the one who's guilty of the sigma algebra of events. Okay? So with Wiener measure, so a model of the noise that preserves the measure, which is called the driving system. Example, Wiener process, and a mapping, which in the random setting is called the co-cycle probability. So map, this is where the time sits, and this is where the probability sits, and this is where the actual thing that we're observing, the x, sits. And, well, example, the solution operator of an SDE. And so the co-cycle property, which I just called in general the semigroup property, just says, okay, so here runs your realization. So this approach to randomness is different from the usual forward Fokker-Planck approach. Okay, it's called sometimes, to distinguish it, the pathwise approach. The particular realization is running here along in omega. And these are the fibers of the bundle. So in other words, the realizations of your phase space for a particular value of your random process. And the semigroup property just says if you go from here to there and from there to further, it's the same as going directly from here to there, which is written down here. Okay? And so this is in more rigorous language. So in that very simple example, the pullback attractor was just a straight line which you can compute analytically. Franco took a very simple example of sinusoidal driving. And this is a more general attractor. And again, it just shows that you pull back in order to see what happens at a certain cross section, which we called in our earliest paper, not knowing about, although I personally knew Chelsea-Grebogi and I thought I didn't know that paper, so we called these things snapshots, which is a natural thing. Okay? So for each one of these snapshots, you have to pull back, let it rip, and it converges onto it, and it does so basically in finite time rather than having to go all the way to minus infinity. Okay? So now, what I was saying before, when do I have to finish?
You have 15 more minutes.
Yeah, okay. You know, tipping points are first a very effective rhetorical device. You know, we've had bifurcation since Euler, who did the buckling problem, okay? But bifurcations, you know, it's a Latinate word, as you say in English, and anything that is polysyllabic and Latinate doesn't sound threatening enough. While tipping points does. It's Anglo-Saxon, you know, so. But there is actually a meaning, which is very nicely described by Peter Ashwin and colleagues in this paper, in which what we were just talking about as being the adiabatic change in a parameter can be handled in a more, again, self-consistent way. And there are three kinds of this. So there are bifurcation due tipping, a slow change in the parameter leads to a system passage through a classical bifurcation. Noise-induced, again, random fluctuations lead to the system crossing an attractor Bayesian boundary. And finally, rate-induced tipping, which is one that maybe was least well known before. Rapid changes lead to the systems losing track of a slower change in its attractors. So all three types of tipping involve an open system. So we start, okay, so this is what I do in general when I have more time. Okay, climate applications. Lorenz, Laura, and then Enzo. Okay, so when we became interested, in spite of the fact that this literature on random attractors goes back a couple decades, okay, the best realization of a snapshot of, first of all, there was only a snapshot by Schmalfuß in Zeitung für angewandte Mathematik, which was even much cruder than this one. So what we're talking about is a snapshot of the random attractor for the Lorenz system with multiplicative noise at the standard parameter values of the butterfly. Compute a fixed time and for the same realization omega. made of points, as I said, transported forward, and even computed pathwise. This object supports meaningful statistics. So this is at a much higher resolution, and again, this was originally computed by Eric Simonet, sitting here, and has been shown since many times. So we compute a probability measure at some fixed time for fixed realization, and we show a projection. So this is Z and this is X. And the dW gets multiplied by a coefficient alpha and X, Y, and Z in each one of the equations. So this is, unfortunately, there was a different choice of colors and of ratio, but the important thing is that this is not a small perturbation theory. Alpha here is 0.5, okay? So in this direction, the Lorenz attractor is a little bit bigger, but in this direction, it is order 1. So this is non-negligible, and what you see is that unlike in the cases that were analyzed before, for instance, by Yuri Kiefer, where additive noise will just smear out the contour set structure of drilling through the onion skin, you have here, the theory says, and you can verify numerically, that the invariant measure that is shown here is singularly supported on the unstable manifold of the deterministic attractor, essentially. Okay? So this is just a snapshot out of the supplementary information in this paper, but Mikhail has now put it as a Vimeo movie on his website. So many of you who have sat through some of these before have seen it, but it is still pretty spectacular. Okay? So let me show it to you. Okay? I think Denise Shamahala is giving the last talk on Friday, and she will talk more about the topology of this stuff. So you see that on the one hand, you do see still the underlying the Lorenz butterfly, but the noise interacts, so there's a certain jitter in the movie, which is just the effect of the noise. But then the coupling between the noise and the nonlinear dynamics is entirely non-trivial and very exciting, and very much still an open question. Okay, so we're trying to make a little bit of headway on sorry. No, that's not the one that I wanted to minimize. Okay. Okay. So, sorry. I think that I went too far. Okay, yeah, sorry. Okay, sorry, I don't know why this jumped, but okay. So here we are. So now ENSO, so again, physically this is what it is. A change in sea surface temperatures in the tropical Pacific, and the change of depth of the thermocline. So again, since I'm nearing the end, I won't go into the details. These are two time series that characterize the state of the tropical Pacific. One is this average of sea surface temperatures over a certain area in the eastern tropical Pacific. The other indices, 3.4, etc. Never mind. The SOI is the seesaw of sea level pressures at Tahiti and Darwin. And these two things are clearly just incredibly anti-correlated. So it is very clear, although there were silly attempts when deterministic chaos became popular to declare that all sorts of climate things were actually fractional dimensional and low dimensional. That's clearly not so, but what you see here is that clearly a lot of the variance is just in some large scale stuff. Right, Feifei? Okay. So if you just try to model the large scale stuff, okay, this is, again, out of, well, at the time we couldn't publish really this color picture, but it's out of the Ghil paper in Physica D96. And basically this is a parameter that has to do, that essentially fixes the periodicity of the intrinsic period. And this one is a coupling coefficient between the atmosphere and oceans. So this is a well-known quasi-periodic scenario of transition to chaos. So the various colors represent period, period 1, so just a seasonal period, 2, 3, 4, and 5. And where you have overlap, you have chaos. And then, so this was the first one. And then in this one, we use the standard circle map or Arnold map, Arnold with a Miyake Znak, where you see the devil's staircase and you see the effect of noise. So in other words, the PDF, which is clearly, at this level of nonlinearity, is discrete. There are separate peaks because the PDF becomes multimodal but connected. And now in this work, we are trying to look into the details of the effect of noise on the Arnold map with, for instance, changes in the fact that the devil's staircase is no longer monotonic. Okay? And to follow up on this, if you have two coupled Arnold maps, it looks even more exciting. And again, the effect of noise, we never got to publish this, but the effect of noise on this is also smearing out basically what's going on. Okay, so this comes, the quotation mark comes from the fact that I got a certain award of the EGU, of the European Geosciences Union, and the press agent told me I have to attach some big words to it for the press conference, so here it goes. Classical strange attractor, physically closed system, model mathematically autonomous, neither deterministic nor random forcing. So you can think, if you can think of humanity as being deterministic, well, you can associate that with the warming trend. Nor random, things like volcanic eruptions or the effect of clouds. The attractor is strange, but still fixed in time. So again, people don't like things they're not familiar with, so it's strange for the same reason that an irrational number is irrational. It's a curse word. Okay? So climate sensitivity change in the average value first moment of the coordinates x, y, z as a parameter lambda changes. Well, this is out of an encyclopedia article of Lenny Smith. You have in systems of interest in climate, you have coarse graining that has been discussed here. And basically, in this case, you have at least a long transients of coarse graining. You start with a PDF concentrated at the origin, and you move in time like this. And eventually, it will be unimodal here, but for a long time, it's bimodal. Yes? Okay. So, now come the snapshots of what I showed you. The attractor is now pulled back and evolves in time. Okay, climate sensitivity change in the statistical properties, first and higher order moments of the attractor as one or more parameters change. Okay, and so here you have, Lorenz says climate is deterministic and autonomous but highly nonlinear. Hasselmann says climate is stochastic but quite linear. Trajectories decay back to the mean and you have full synchronization. Grand unification, climate is deterministic and stochastic as well as highly nonlinear. Internal variability interact and forcing interact strongly. Change in sensitivity refer to both mean and higher moments, distribution of extremes, etc. So I will have to skip this, but promise you that Denise will tell you much more about Laura's topology. I don't want to steal her thunder, but just to keep you riveted to your seats till the end of the workshop on Friday. The answer is that it's, of course, as you might have suspected from the video, the topology is different from the classical one of the butterfly, and it changes in time. Okay, so you have what Yuzuru called topological bifurcations. Okay. So, sorry, and the dependence on parameters is not smooth, and okay, so there are other ways, and this is just to say that within a global pullback attractor deterministic case, there can be local ones with very different properties and probably with fractal basin boundaries. We've heard about such things yesterday, and you can look it up on Stefano's website, the full talk that he gave here last week, and he's still here to discuss it with him. Okay, and this is just the 2 slides out of what Denise will show you. So this is just a definition. It turns out, again, that Poincaré contributed to the 2 important aspects here. One is creating algebraic topology, and the other one is figuring out chaos in the context of celestial mechanics, and even stating that probably the same cases. The same case is for weather. Okay, so these are just you know, 2 different snapshots of the topology. Okay, so concluding remarks: change of paradigm from closed autonomous to open non-autonomous system. Random attractors are spectacular. I think they are useful, and they're certainly just starting to be explored for climate applications, although with a lot of enthusiasm. Here's some of the work in progress. Study the effect, study the effect of, usually when you have a stochastic parametrization, like previously deterministic ones, people just test because whether it does what you wanted it to do, modify a particular aspect of a general circulation model's behavior, but people haven't looked at the effect on a lot of the other things, which is not always favorable. Applications to intermediate and high-end models via empirical model reduction and such methods of what's called now deep learning, but again, it's something we've had around for a while. Applications for climate sensitivity and even for predictability, which I didn't have the time to talk about. And so this is some of the references with those I'd like you to to look at more closely emphasized. And of course, you wondered whether you already showed yesterday, and which, you know, appropriately was deposited on archive just a few days ago. Okay, thank you very much.
Okay, comments or questions from the audience? Yes, Roger.
First, a main question, and depending on your answer and the comment, is a random attractor always something with multiplicative noise or not? Because as you said, when you have just stochastic noise.
Well, it doesn't have to be. When I showed you the equation, you know, I did put, I think, sigma of x in front of the dw, but it doesn't have to be. Well, you know, the properties might be different. I mean, clearly the properties of, you know, the interaction that you've seen between the dynamics and the noise has a lot to do with, but it can be interesting even otherwise, okay? And I think that actually at least some of the examples that Yuzuru showed you, you know, the noise was not multiplicative, right? Yeah, so the short answer is yes. That multiplicative noise is everywhere. People deal with additive noise because of lamppost syndrome, because it's much easier to deal with. I mean, noise is not, you know, first of all, I have another slide. I kept just a few reserve slides, you know, but here, nature is not deterministic or stochastic. It depends on what we can, need, and want to know, more or less detail with greater or lesser accuracy. Well, typically larger scales more accurately, smaller scales less so, but we need both descriptions, okay? So, you know, the multiplicative is not special. Additive is special, but it's under the lamppost, okay? Yep.
I'd like to make this note that the economic community seems to have a correct understanding of the force response, so define it also in terms of ensembles, and nowadays there are modeling groups which generate these large ensembles of 100 members, let's say, in Earth system models, but they don't seem to know about Ludwig Arnold or Gabogin and Romain Ras. But it seems to be that these ideas was injected into the climate community, specifically by Cecil Lee. He has a paper in 1978.
But sorry, can you repeat? Speak up. Actually, we should use the.
Yeah, we should use this. You have to now run up to turn on.
No, I'm not going to run. No. This is too much. That's against my religion. I'm sorry. Stop this.
Thank you, Oliver. So I just wanted to mention this name, Cecil Leith, since we have a long list of references about non-autonomous systems. There is a paper in 1978, actually in Nature.
Who is this?
From Boulder.
Oh, okay.
Yeah.
Okay, well...
and is defining the climate in terms of ensemble-wise statistics.
Well, but that's not the same thing. You know, they're always precursors, but just doing, you know, just running an ensemble forward in time. I mean, again, I've told already this joke a few times since the trimester started, but there is the play by Molière, you know, which is called Le Bourgeois Gentilhomme. You know, the burgher who wanted to be an aristocrat and who gets a lot of teachers. He wants to learn dancing, and one of the teachers is a teacher of literature and tries to explain to him the difference between prose and poetry. So Monsieur Jourdan goes, oh, so I've been speaking prose my entire life. You know, so yes, people do ensemble runs, and, but they do not necessarily quite understand. You know, I'm sorry, you know, the fact that you need two parameters for the non-autonomous situation. In other words, if you have, in the autonomous situation, if you have uniqueness, you know, you can just do forward asymptotics, but here you need this other parameter which takes you back in time. And you really need to define the convergence of what you observe with respect to that again and again. You don't just run the ensemble forward. In order to properly define the pullback, you know, you stop at the time, you know, when you want to observe it, you have to pull back, fortunately just a finite time, and not all the way to minus infinity, and you have to go forward again to really define the object. And again, I'm sorry I didn't have the time here, and I don't want to, you know, and Valeria won't let me to cut too much into the coffee break. But for instance, the work that we did with Ilya Zalyapin, which was published in an AGU monograph, is we took another ENSO model, also one of these delay differential equation models, and well, he computed. Mikhail was also, no, actually he felt he hadn't done enough to be actually a co-author, but anyhow, there's part of the paper that, or the chapter that's due to him. So Ilya computed a pullback attractor, and it teaches you a lot more about the stuff than just looking at a video of a forward run. Okay, so I still would like the reference if you can send me an email, and you know, but there's a real difference in understanding between, and I don't care at this point whether you use snapshot or pullback or random or whatever, but the understanding is that in order to really define what's going on, you have to follow the evolution of the attractor and not just of a trajectory, yes, or even of an ensemble of trajectories.
Okay, thanks. Other comments or questions? Okay, then let's stop here. Thanks again to Michael.